all, let me make the field trip. I am planning to join it, but I'm not really sure we can. But for sure, it will substitute anyway the lecture that we have. So then we jump to the last one. The last one will be actually May 13. It's in the calendar on my website. I think 13 or 14 May, yes, because so 20, just 1 second, I check. I think let me go on my website, very good. And then it's lecture notes and then actions. I think there is the last one, May 20. Okay, why not? Okay, yeah, I understand why. Because May 13 is, I cannot teach. And so May 20, very good. So it will be the last one. There will be a seminar of one of my PhD students focusing on random forest modeling, so machine learning. And then I will finish with 1 hour of lecturing by me. And that's it. And now let's go to our lecture today, which is continuing what we have already introduced. We introduced deterministic models. And we made the example of climate models, but this was made earlier. And then we focused with more details on the bucket model, to give an example, and then machine learning. So machine learning, actually, I already introduced it. I just would like to say once again that it's the engine of artificial intelligence. And artificial intelligence is very new, but artificial intelligence in the way we mean it, like ChatGPT, or it's very new. But instead, machine learning is not new. I said that it's about, we can locate around 2000, the widespread usage of machine learning in several branches of science. But recently, with the improvement of computing power, we could apply machine learning to generate artificial intelligence to the exploration of the web. So in the past, machine learning was used to explore data pattern relating data, so patterns relating like global temperature with wind speed at the continental scale, and therefore the application was limited to specific problems. Now, with the advent of artificial intelligence in the modern solution, we apply machine learning to everything, from the web search to finding advice on how to behave in particular situations. Basically, what artificial intelligence does is to explore patterns between categories of data, patterns between information, by using essentially machine learning. Machine learning is a very broad term. It includes several models. Now, so this is the general introduction. Let me stress in this general introduction one key issue. Any deterministic model, most of them, let's say almost all of them, they involve parameters. And we explained what is the purpose of parameters, to make the model flexible and therefore to allow the model to fit patterns. So the model is used to explore patterns, but the way they are explored is by fitting them, so by trying to reproduce them, by building a model that reproduces them. And given that patterns in general have several different forms, then the model, the machine learning model that we use to fit these patterns, that we use to explore these patterns, must be flexible. And therefore, flexibility is granted with parameters. Typically, parameters need to be calibrated or fitted or trained or optimized. There are several synonyms. And in particular, in machine learning, we use the term training, but in hydrology, we usually use the term calibration, but actually they mean the same thing, like adapting a general model structure, a flexible model structure to specific patterns that we are exploring. And so these parameters give flexibility in a way. Usually, once they are trained, they are kept constant. So in the final structure of the model, they look like constants. Like if you fit a linear regression, these constants are the intercept and the slope. In fact, linear regression has two parameters, intercept and slope. So once in a linear regression we calibrate them, they are kept constant normally. But in general, they are not constant. They can be tuned, calibrated. And the way I used to define what parameters are, I say they are degrees of freedom. They are coefficients that are included into a model to make the model flexible. And this is the premise. What is the main difference, the main news in machine learning? Machine learning, they try to get rid of the concept of parsimony. What is parsimony? Parsimony means that a model uses the least possible parameters. So the number of parameters is restricted, and therefore the model is called parsimonious. In the past, we were indeed very attentive, very rigorous on parsimony. Why? First, to avoid computational problems. So reduce the number of parameters to be trained means reducing the burden, the computational effort. This was the first reason. The second reason was that we were used to deal with limited data requirements, limited data availability, sorry. And therefore, you understand, in order to fit a parameter, you need data. You need data in order to train the model. So basically, you compare the model simulation with the reality that we observed. These are the data, the reality. And then we try to find the parameter values that match in the best possible way the simulation with the reality. That's fine. If we have only few data, of course, the calibration training becomes a little bit less reliable, not a little bit, becomes less reliable. And the higher the number of parameters, the higher the amount of the data that you need. So in the past, especially in my field, water resources management, hydrology, climate, our field, climate, we were used to deal with limited number of data, limited sample size, we say, and therefore we tried to limit the number of the parameters. So to give you an example that we already considered, the bucket model. The bucket model, when it's formulated in a linear form, it includes only one parameter, which is the bottom discharge parameter. Rainfall-Runoff models, which I know quite well, when the number of parameters is large, we count like 15 of them. There are some models with 5 parameters, some models even with less than 5, 4. And then the max number is about 15, because we were very attentive to parsimony. In machine learning, the idea was, let's get rid of the concept of parsimony. Let's try to explore the performances of models with a large number of parameters. Why? Because indeed, when machine learning was first used, it referred to fields where the data available are very many. So large sample sizes of training data. And therefore people said, why should I care about parsimony? Because this is quite clear. If you increase the number of parameters, you make the model more flexible, the fitting of the data improves. And let me just try to make a very it increases uncertainty. Yes, it increases uncertainty. This is what we already discussed. Let me just make a little bit of a sketch, but I'm coming to uncertainty a little bit later. Okay. So basically, if I have a pattern to fit, like a very simple, let's say, y, x, where x is the independent variable, is the explanatory variable, and let's suppose that we have this kind of pattern. which shows a general increasing trend, but there are also there is also some variability. Of course, if I fit a linear regression, the linear regression looks like this. And this is perfect, okay? And you see that I fit the general pattern, but there are several simulation elements in the simulation. The distance between the observed data and the simulated data by the linear regression, it's up and down. The simulation is not very precise. Now, let's suppose that this pattern is described by 100 observations. So 100 sample size, okay? Sample size. This means that my model is relying on observed data. So this is X, okay? So observed, and this is X. It's X1, X, Y, sorry. Y1, Y2, Y3, okay? And here, let's say, this is not that's fine. X, yeah, X may be time, but anyway. And then this is the observed, and then there is the simulated. And the simulated is like Y hat 1, Y hat 2, okay? And then we try to make the Y hat as close as possible to the Y corresponding observed Y, okay? Let's suppose that I have 100 observations. So here is Y at 100, and here I have Y 100, okay? Now, let's suppose that we create a model with 100 parameters, and the relationship is very simple. I put equivalence here. Okay, so my model is Y1 is equal to, or let me say, it's not a good example in this way, sorry, one second. The relationship is Y1T X, Y2X, Y3X, Y1X, okay, and here we have at X, up to X, etc. Okay. So now, if I allow the model to count 100 parameters, I am allowed to get a perfect simulation of the pattern, a perfect reproduction, because I can say, I can find a relationship that allows me to reach the target of equivalence, okay, equivalence. I can find a relationship because I may simply say that for each of the observed data, my relationship is equivalent to equate the simulated data to the observed data. So I reach a perfect fitting. On the other hand, this kind of relationship is taking a different value at each step, and I can estimate it only if I have the availability of the observation. If in the future I don't have the corresponding observation because Y is unknown, I cannot extrapolate this observation. And therefore, there is, of course, in the future, the largest possible uncertainty because the model is not able to make any extrapolation. And this is why we try to reduce the number of parameters. This is why we say, usually, let's keep, let's take a model with the a number of parameters that is at most 1/10 of the observations, because we want to find something, a relationship that is more independent of the availability of observed data. So, from this example, you understand that if you increase the number of parameters, and the number of parameters is increased a lot, like equating the number of data, you can perform the training in a perfect way, but on the other hand, you don't have any information for predicting the future, and therefore you have the largest uncertainty, which corresponds to computing the mean and then making a prediction that is equal to the mean. And this is the reason why we try to limit the number of parameters. On the other hand, it's people who started using machine learning, they had a large amount of data, so they could increase the number of parameters while still keeping the number of parameters much lower than the sample size of the observed data. So they felt like, why should I limit the number of parameters to 10 if I have 1 million of data? I can, anyway, increase the number of parameters. If I have 1 million of data, even if I get 1,000 parameters, that's fine, because the ratio between parameters and data, so sample size of the parameters and sample size of the data, is still very large. 1,000 parameters against 1 million data means that the ratio is 1/1,000. So, I mean, they introduced models that basically forgot about parsimony. But suddenly, what happened was that when these models were applied to disciplines like environmental sciences, like climate change, it emerged a problem. And the problem was that these models performed very well in prediction. Perfectly. So the training was okay. But when they were tested with a validation, and in machine learning, they use different terms. They also use testing, which is something in between training and full validation, where full validation is emulating a real world application where no clue of future observed data is available. So when they were tested against a future that was completely unknown, machine learning showed larger uncertainties, which is what one would expect. And this is called overfitting. So if you look over the web for overfitting, this is a part that is not yet described in my notes because we dealt with these calibration issues in the first semester. So, and let's see in English, overfitting English. Overfitting, Wikipedia, in mathematical modeling, overfitting is the production of an analysis that corresponds too closely or exactly to a particular set of data and may therefore fail to fit to additional data or predict future observations reliably. An overfitted model is a mathematical model that contains more parameters that can be justified by the data. So this is saying, in other words, what I already said. In the special case of a model that consists of a polynomial function, which is parametric, these parameters represent the degree of a polynomial. Okay. The essence of overfitting is to unknowingly extract some of the residual variation, like noise. Okay, noise, I think you understand what it means. It's something that is completely different from the signal, yeah? As if that variation represents the underlying model structure. So overfitting means that the model structure is trying to gain an interpretation of the noise, which is not possible. And here there is an example. So here, the red and blue, what's the difference? Let's see. And the green line represents an overfitted. Okay, I understand. So we have points that are the red and blue. Okay, and the observation. Okay, basically, this is a model. The black line is a model that is not overfitted, while the green line is an overfitted model. I still don't understand in this figure what is the difference between blue and red points. I see that they are sitting the blue on the right and the red on the left of the green line, but still, it's not really a problem. What is, I think, nice here and is to see clearly that the green line is more difficult to extrapolate because it's going up and down, and it's really difficult to get an interpretation. When you see such situations in Wikipedia, to gain more information, one may try to look, to click on the figure, and then look at here, more details. Okay, here now we are in Wikimedia Commons, and the figure from Wikipedia are taken from Wikimedia Commons. Wikimedia Commons is public domain. Let's see if there is more information here. I don't think so, because usually they put here a caption, and there is no caption. So I don't think it is really easy to understand. I understand the difference between the blue and the red, but the difference between the points that have the dark, the black circle around, I don't understand what is the meaning. But anyway, let's not to lose time on this, because maybe that while the green line best follows the training data, okay, it is too dependent on the data and is likely to have higher error rate on new unseen data, illustrated by black outline dots compared to the black line. Okay. Yeah, anyway, I think that these points are closer to the red line. These points with the black circle are closer to the red line than to the green line. But I see that there are others. Anyway, let's forget about it. But anyway, we understood what overfitting means. Okay. So now, when we start talking about machine learning, we have to be aware that we will see a clear difference with respect to the models that we considered so far, like the bucket model, that the number of parameters is large, as you will see. And therefore, and then we have to keep in mind that once we present something that was computed with machine learning, we need to face the very likely question, what about overfitting? And this means that if we want to compare a machine learning model with another alternative that is more parsimonious, we don't have to restrict the focus to the training data. We also have to refer to validation in order to be able to reply to the question about overfitting. There is also another issue here. Machine learning, the models are many. They are not very easy to be understood because they don't rely on a physical law strictly. They don't rely on a conceptual figure like the bucket. So basically, they have a structure that is dictated by the target of fitting the data. Understanding this structure, then, it's not easy. It's not like looking a bucket. I show you a bucket model. You will see that when, in a minute, I will show you a scheme for a machine learning model, the interpretation is a bit difficult because they are a bit complicated. So there are several computations, nested computations, one inside the other. It's a bit difficult. And at the end of the story, it's not easy to understand how they work, what is the number of parameters, and what is the reason why they choose a particular structure. It's not easy. So if we are asking the question, why you selected that type of machine learning instead of another one, then the reply can only be because the fit was better, because the performances, even in validation, were better. But this may be like a step back with respect to providing a physical explanation. So this is the criticism towards machine learning. And this challenge of understanding is reinforced by the widespread availability of several softwares allowing us to model with machine learning. And these are very easy because basically what you need to do to deliver to R or to Python is input data, output data, and that's it. And they make the computation and the fit is perfect. But most of these softwares don't tell you warnings like, be careful. You are fitting a model with 1,000 parameters on 100 data. Be careful. Or they don't give you the number of parameters. I really struggle. I had to ask ChatGPT, what is the number of parameters of this model, just in order to understand. So the fact that they are complicated, the fact that we have a software that is really available makes them, I mean, a bit risky in terms of scientific contribution to your education, because you are simply using a black box without understanding what the black box does. So, and it's also a bit risky from the point of view of the applications, because the literature recognizes that there is still an open question about machine learning. What is the uncertainty? Actually, I think it's not so open, but anyway, the literature recognizes that it's a challenge. On the other hand, because it looks like I am criticizing machine learning, on the other hand, artificial intelligence as we mean it today, I mean, applies machine learning and it is successful. So now if you make a search or with ChatGPT, it's much better than the previous Google that we were used to, because you have to check what happens. And why you need to check? Because there is uncertainty indeed. And so you need to check. But on the other hand, their power in providing, in giving interpretation of what they find on the web proves that the solution is valid. On the other hand, you have also to keep well in mind the risks. In particular, if you are a young researcher trying to provide meaningful contributions in science, beware that if you use a machine learning model, you should pay attention, trying to understand what they do. To my students, sometimes I say, look, okay, very nice, but if you had to write a code in R from scratch by using only base R functions, are you able to do that? Because this means, did you really understand what it does? Because what they do is very simple. It's very simple. The only thing is the workflow, the interpretation of the workflow. And very often my students say, no, really, I use the software. Or my question sometimes is, how many parameters here? And the students can hardly reply because the software don't give the answer. So just beware of that. But on the other hand, and this is what I say to my colleagues that are older than me, because I mean, they are critical on machine learning because they say there is no physical basis. So mass balance is not respected, energy balance is not respected in their interpretation, not necessarily. On the other hand, I say, my reply is, okay, look, are you using ChatGPT? Yes, I am using it. So it uses machine learning, and you see that it works. This means that provided we have enough data to calibrate them, mass balance, energy balance must be, of course, recognized by them. Because if they work, it means that they preserve mass, they preserve energy, of course, in the presence of uncertainty. So, I mean, when you compute mass balance for any real application, you see that there is an error because you don't know very well the inflow, the outflow, there is uncertainty, and therefore that's it. Okay, but now let's try to give an example. And the first example that I'm giving, I just picked it up by chance, is related to random forest. Okay, here you see the word random. So you may say, why we are talking about deterministic models. Why are you providing this example? Because at the end of the story, the random forest model is a deterministic model. And even if you see you will see there is some randomness, at the end of the story, the output is deterministic. So it is considered to be a deterministic model. It doesn't provide the probability distribution of the output. But let's see how it works, because I think it is an excellent example, because it's relatively easy to learn it. So first of all, random forest can be used for both classification and regression. What does it mean, classification? It means that you have observations of something and you want to classify them. Classify means assigning categories. Okay, very simple. And it's even simpler than regression. Regression, we know what is. You have a set of explanatory variables, maybe more than one. In the simplest case, it's one, like here. And then you have a dependent variable that you want to explore. Explore means finding the best relationship between X and Y. Okay. Okay, very good. And the decision is taken by following a decision tree. What is a decision tree? Let's look at here. And this refers to a decision that I take every day, almost every day. Like, I found this picture on the web. Can I publish it in my website without asking permissions or not? Okay, so let's start from a first question. Okay, this is a first split of the data. It's a first node. Is the picture more than 100 years old? Yes. Okay, take this direction. Okay. And then, no. Okay, take this direction. So let's take the red direction. Did you create the picture of yourself? Second split. Yes or no. Let's take yes. Okay, I created it myself. Fine. Next question. Do you agree with uploading your work to either public domain or under one of the Wikipedia free licenses? Very good. Yes, I am willing to. Okay. If you say no, then it stops because, like, okay, if you are not willing to, what's the purpose of making asking? Okay, so can you then, let's suppose yes, I'm willing to. Another decision. Can you for sure deny third-party rights? Because this is relevant. Sometimes I make a figure, a picture myself, but I use like a small piece, like an arrow coming from the web. And then I have to ask myself, can I put this arrow, this icon into my figure? Can you for sure deny third-party rights? Yes, go ahead and do that. And then we got to the leaf, the leaf of the tree. These are the leaves of the tree. The leaves are go ahead, do not upload. And then you can follow the other pattern, okay? Like, did you create the picture yourself? No. Is the author or owners known? No, do not upload. Yes. Is the author dead for more than 70 years? No. Did all owner or rights agree with publishing the picture? Yes. Okay, go ahead and load up, do not upload. This is a decision tree, okay? And of course, this is a kind of classification, I would say, because we are classifying the pictures in two categories. Go ahead, do not upload, okay? And these decision tree are much used in decision theory. This is not a new invention of the random forest algorithm. On the other hand, you can understand forest means a lot of trees. So probably you already understand that the random forest uses a lot of trees. This is true, but let's see what this means. And keep in mind that in some cases, but this is something that is not interesting to our discussion, the splits may be regulated by also probabilities, like we can estimate a probability. Like, did you create the picture yourself? Is not a good example, but I could estimate a preliminary probability, like it's likely that people didn't make the pictures themselves. And then we can also associate costs at any step, at any branch of the tree, so that you end up at the end with an estimated cost for going ahead and an estimated cost or like loss if you, at the end of the story, you cannot upload the figure. Okay, so there are several variants. Okay, very good. Now, let's make an example here at this stage. And the example, let's make it, I created it, it's very simple. And let's refer to what could be our problem, okay? And the simple example where indeed we have to make a regression. A variable y is to be regressed against a single explanatory variable x. With single, I mean a single vector. So basically, there is a regression of y depending on x, and we may have more than one explanatory variable. But for now, let's try to identify our challenge with this question, y fx, and we have to estimate the shape of f. This is equivalent to say I want to inspect a pattern of the relationship between y and x. And then y and x are vectors, and they are vectors including lowercase m, paired observations of x and y. Okay, we have the sample size of our data is m. Very good. Now, what does Forest do with this example? Let me make a sketch on the blackboard, and then we will look at the web page, because the web page doesn't include the sketch, which I didn't have time to. Let's see if I can find the relation that works a bit better. This one is a bit better. Okay, good. Now we have x and y. Perfect. Now let's put the x here, our data. Okay. Instead of the dots, you can see numbers here. What is important to say is that let's put them here in ascending order. The x order. And now here we have the corresponding y. And these are in order, then order of ascending corresponding x. So the y's are not in ascending order. The x are in ascending order. And then we order the y by associating each y with the corresponding x observed at the same time, for instance. Okay, so these are not in ascending order. Okay. Now, let's make a first split because the tree works with splits. And let's fix a threshold t here, t, so that here we have x lower equal t, and here we have x greater than t. Okay, of course, because if this is in ascending order, then I split the data, okay, and of course the data at the left are lower or equal than t, and these are larger. And therefore this split is also reflected on the y's, which again are not in descending order. Okay? Now, here we can compute the average of y, and here the average of y. Let's say, let's denote it average y1, average y2. Average y2. Okay. Perfect. Now,
Both of them on 1, 2.
no, one. Thank you. Okay, now what we do is let's take this first data here. Okay, this data is on the left of the threshold, is in the first group of X. Okay, perfect. What is the model prediction then? The model prediction is given by average y1. This is my model prediction. So this is x1 half. Sorry, y1 half. Okay, let's take another observation here. It's in the first group. Once again, this is my prediction. And this is y n hat. So to all the data in the first group, I give the same prediction, it's the average. Okay. Same thing for the data in the second group. Y n up n1 hat. So with this very simple scheme, for each of the observations, I get a corresponding prediction. And then, of course, I can compute. Remember, I have n observations. N observations. Perfect. I can compute 1 over n, 1 over n y, I sum I equal 1 to m y I minus y at I squared. Okay, and this is what we can call mean square error. It is simply the sum of the squared deviations, which I have computed in this very simple way. And of course, I will get an approximation. It's not perfect. Okay? It's not perfect. Now, what could we do at this stage? And we could say, okay, I took the threshold at an arbitrary value, and I got this error. What if I move the threshold? Okay, so the machine learning training means finding the position of the threshold that minimizes this. And look, this tree, we say that this is a tree with depth 1, why depth 1? Because there are only one threshold here. What would I like to say? Okay, the fitting is not very good. And it's clear, in my understanding of this very simple model, that if I put another threshold here, T2, which means, sorry, T1, which means that the depth becomes two now, because I have two thresholds. And this means that also here I have another group of y. And therefore, my representation for sure improves in training, because clearly I compute the average of a reduced number of data, and when I allocate each data to the average, I get an improvement. Think of, if m is 100, think of putting 99 thresholds, which means that when I train, any observation goes to the corresponding value, and the mean square error becomes 0. So you understand that, indeed, two things. First, if I increase the number of thresholds, this representation improves for sure. And second, it's clear from this example that if you get a number of parameters that is the same than the sample size, you get a perfect representation. Now, this is a random forest. And then you may say, why random? Well, random because random forest makes elaborates indeed a great idea on this. What is the great idea? The great idea is that they thought of something like, okay, I have these observed data, but what if I had less than that? So what would be the structure of the tree? What would be the position of the thresholds if instead of 100, M100, I had M90? So the idea is, let me try this experiment. I take the same vector x, I remove like 10% of the data with replacement. This means that if I remove replacement means this. Let's suppose that I have a vector with 3 numbers. Okay, I remove this and then I randomly pick up to substitute this to keep the same sample size. I randomly pick up a substitution from the first or the third. So this means that some of the data are replicated, which means that the variance is reduced. So the information content is reduced while keeping the same sample size. And then they repeat. But this extraction, this elimination of the data is randomly done. And therefore they repeat the estimation. And of course, you find a different pattern. And it is a good thing because it means that you, in a way, assess the variability of the model with respect to the information content. And then they elaborate a number of trees. This is a parameter that you can fix in your model. I want 1,000 trees. And the end of the story, your prediction is the average of the predictions. I didn't talk about predictions. Prediction means that once that you get a new observation of X, you follow the tree in order to get the prediction like you did during training. With the difference that during training, you pick up the data that you use to tune the parameter. In prediction, you don't pick up this data, you pick up something different. And then you go into the groups, you follow the tree. And of course, there is a limitation if you go outside of the range, but there are algorithmic solutions in order to extrapolate. And you could put, for instance, if you get a value that is lower than the minimum of X, you put it anyway in the first interval. Okay? So this is why random. But at the end of the story, the prediction is given by the average. And therefore, it's deterministic. Okay, good. This is very simple. Before we look at the website, You may have also a second explanatory variable. This means that you may have here another area with explanatory variable C. Okay. And then what you do basically is you travel from X to the corresponding C, and then to C to X. Like, for instance, you could consider like Z may be also like the season, the month. Okay, so you want to identify a relationship between X and Y that depends on the month. So what you do is you start from X, you identify the month, and then you go to the Y. And then when you compute the average, is the average of only the Y corresponding to the X observed in this month. This is your prediction.
And Z here, Z acts as a boundary condition.
No, it's not a boundary condition. It's just an additional regression. It's an additional explanatory variable. Okay. So basically, when you compute the average of the Y, you compute the average only of the Y that satisfy, that are associated to X and satisfy this relationship associated to the set that you choose. Of course, here it doesn't become really regression because the sets are not order in ascending order. You have, for instance, if it is the month, you may have January here, and you may have January here. And that's it. You have another January here, and another January here. So basically what you do is, I start from the X from here, and then all the X that are from here, in this case, I pick up only the Y that were observed in the month 1. Okay, so the average becomes computed on these two values, not the full values. Okay. And of course, it may happen that you don't have any months here because months is a restricted number. And so the way it develops, it needs to be adapted to the kind of data that you have, because it may happen that for the X in the first interval, you don't have any observation in January, so you cannot compute Y. And therefore, in this case, it means that you need more data for training, or maybe that the variable X in that interval in the month 1 doesn't exist for some reason, because, for instance, the river is dry, and then you need to, in a way, to adapt the computation. Now, this is what is written here, okay? And this is the computation of the error, and then in prediction, any input value X minus the threshold is then assigned an output value Y equal to the average Y1, and then in the other case, in the opposite case, it's Y2, okay? Perfect. Now, here in general, the depth of the tree may be larger than 1. This is fine. And here it is explained that instead of relying on a single decision tree, a random forest constructs a large number of decision trees. Now, this substitution of data with replacement, it's a process that is known as bootstrap or bugging. Bugging is used in the machine learning literature. Bootstrap is used in a wider sense. Bootstrapping is a procedure for estimating the distribution of an estimator by resampling, often with replacement, one's data for a model which is estimated from the data. And therefore, Bootstrap allows to, in a way, to estimate uncertainty. And indeed, in this case, it allows to explore how the prediction changes depending on the data available. Very good. Now, this is a sketch that doesn't help much actually, because it is not very specific, but basically you see here that you have a data set, and then you split the data set in 3 groups basically it's not in 3 groups. This is a data set that is randomly sampled to produce a decision tree 1, decisions of 3, decision trees, and then you take the averaging. The majority of the voting is chosen in the regression, in classification. In the regression, you compute the average by the values given by the different trees. In classification, which means that I have to classify the data, so to say if a sentence is false or true, then you sample many trees and you take the majority of the votes. If the majority is false, your prediction is false. If the majority is true, the other way around. But this scheme is yeah, of course it is meaningful, but it doesn't help much. I think that instead what helps a lot is this Python code. It is using a package that is called Sklearn, and it's here. And the Sklearn ensemble is a part of the package, but in Python we have to upload this one. In Windows I tried, but I didn't succeed to get it. And so let me see if I can connect my PC. And then I'll show you how it works. I think it is nice because it allows us to make some experiment. It seems that it is working. Let's see. Mirror displays. Close. Oh, not really. Let me see. Oh, yeah. No, because it's very small. I need to change the resolution just one second. So first of all, let's go here. Very good. And but I need to change the resolution. Display. Okay, perfect. Now let's see. Mirror. That's okay. Apply. Let's see if it works in this way. Let's keep this configuration. Okay, very good. Okay, now yes, it works perfectly. Okay, so let's take the code here. You can see it well, okay? Yeah, on the screen there, it's perfect. Okay, now what I need is terminal. And let's put the preferences at okay. Okay, let's try to should be here, but I can't find the scroll back. No, here there are no fonts appearance. Okay, sorry. I didn't find it at the first. Select. Okay, good. Maybe it's too large, but if it is too large, then we can. Okay, Python 3. Okay, very good. And now let's take this import NumPy, matplotlib and okay, cut and paste. Okay, everything is uploaded. Now here we generate data through a sinusoidal function plus noise, because here there is the generation of 100 numbers with a Gaussian 0, 1, and then we take the scene and again a random noise. So let's make it. Now it's generated, later on we plot it, and then here there is the random forest aggressor. Sorry, I
Professor,
yeah,
Professor, I'm not sure if Professor is sharing the screen.
yeah, correct, because I am not connected with, yeah, this is correct. So let me see, I think I can try to share the screen from the notebook. Give me 1 second. Okay, let's see. Let me check. Okay, good. Now I can try to share this screen. Okay, I think now you see the correct screen. 1 second, I need to go here. Now you should see the code instead of, I think now you see the code. Do you see selected text now? Just 1 second.
Yes.
Very good, perfect. So let me see, the last instruction was, okay. Okay, so now we define the model, random forest regressor. I don't remember what n estimators means, maybe it's the number of thresholds, but we will clarify it soon. And I think n estimators is precisely the number, the number of trees, randomly sampled, okay? N estimators is the number of trees. And now let's fit the model, sorry. With this instruction, we fit the model. And then we, let's just go step by step. And let's wait for fitting. Now it is generating the trees. Sorry, I forgot. Okay, generated the tree and estimated the model. Remember here the sample size of the data is 100, so it's very few of them. And then we can make the prediction. And there is an X test, which means that we use the same model for which we use to generate the training data, to generate the test data, and then we make the prediction. Okay, and the prediction is done depending on the data for testing that we have just generated. The prediction is done. Now we need to look at the plot, okay? So the plot is made with these instructions. Let's make it. And here is the plot. So in blue, the blue dots are the data that I used for, that I generated. And then, which are in the range from 0 to 5, but they are 100 data. And then there is the continuous line, which is the prediction. And you recognize that it is a step function. It is a step function because basically when you split the data into sub-ranges, into sub-intervals, you assign to similar data the same prediction, because to more than one value of X, we assign the same average value of the Y, and therefore is a step function, okay? And this is the result. Now, what happens if I change the number of trees and if I change the number of thresholds, because the number of thresholds was taken by default. I didn't specify it so far, okay? In fact, now I close the plot. If we go again to the website, it invites you try with the above code the following: an estimator one, a single tree, namely a step function. Let's try them, okay? So what I need to do is here, let's put only one tree, okay? One. Perfect, and now we can make the generation, the fit first, and then the generation and the plot. Okay, you see here it's similar to the version that we got earlier, but you can see here that it's indeed a step function because there is no computation of average at the end of the story. So it's indeed a step function. So simply the dots are divided in sub-ranges in ascending order, and then the average of the corresponding y's is associated to each of them. So it's a step function. Now it's interesting to see, to explore what happens if I decrease the number of thresholds. Okay, so let's close this. And then here, how can I change the number of thresholds? By changing max depth. Okay, so if I say max depth equal to 1, the data are divided in only 2 sub-ranges. So let's then change the model here. Let's keep the number of trees equal to 1. Okay, and max depth equal 1. I should get data divided in only 2 sub-intervals. Let's see. I say let's see because when you use a software, you have always to make sure of what they mean for a parameter. So max, what is their meaning for depth? I think if I say depth 1 means 2 sub-ranges for the data, but let's check, okay? Yeah, you see, it's clear. This is the result. You have 2 sub-ranges. It's a step function with 2 levels. And you can recognize that in the first half, which is not half, is a bit more, in the first part, there is a continuous line that is located at the average of the points. If you see the position of the points and the position of the straight line is on the average. And in the second part, it's the same thing. Okay? So interesting enough. Now, let's try to put let's try to use a max depth, which is the max possible, okay? So let's put it at 99. So let me just keep 1 tree and max depth equal 99. Okay, and now we fit it and we make the plot. It's not really a perfect reproduction. I think that maybe because it is taking a max value of max depth to prevent overfitting, because this is the same value that it was taken by default. So I think, but you should look at the software. There is a manual of the software, Sclern, and I am convinced that it takes a max value of thresholds because it doesn't want to get overfitted. And therefore, this is why we get this, okay? But we can make, and then we conclude. And another example with a depth of 2, so 3 sub-ranges, just to check. So, sorry. I need to, okay. 1 and max depth, oops, max depth equal 3 or 2, sorry. Okay, and now let's make it again. Okay, you see that now the number of intervals is a bit larger than expected, and we should, because now they are 1, 2, 3, 4. Yeah, 4 maybe because we should look at the software. Anyway, you understand that there is some control in the software related to the parameters that we give. Just let me check that I didn't make any mistake, but then I think the concept is clear. No, I don't think I made any mistake. I don't remember if, let's see, let me repeat it because I want to make sure that I didn't make any mistake. Max depth equal to. And indeed, there is one more. Let's see. Yeah, there is one more subset. I don't understand what is the reason, but anyway, it's something that we need to inspect on the manual of the software. But I think the concept is clear. Very good. Now, let me check if I should better take this. Let me just keep the screen here because here there is another simple example through R code. And it's interesting it's again a sinusoidal function. So it's interesting to see if we get similar results. But this is a different story, actually. I tell you why. Let me just first close Python. Okay, quit. Okay, and here I have R now. So let's see this code. This code is a step forward because it includes more than one explanatory variable. And what are the additional explanatory variables? Are the previous data points of the sinusoid. This means that it's a kind of autoregressive model plus an exogenous variable. And first of all, let me see if I have already installed these, because we need these packages. Random forest, you understand, is the R package that is applying the random forest model. And then we need this package, which is an auxiliary package that we need. So let me see if I have already installed them. So we avoid to, yes, they are already installed. So I uploaded through the library command. And then you see how the data are generated. It's time that is varying from 1 to 100. And then the value is computed by a sinusoid plus noise. Okay, and the noise has a limited variance. You see that the variance, the standard deviation is 0.2. Our norm, remember, is the instruction to generate a Gaussian noise, a Gaussian random variable, which is decorrelated, no correlation here. And the size is 100 because I need to add it to a sinusoid that is 100 data long. The mean is 0, the noise, and the standard deviation is 0.2. Okay, and then I need to create a data frame of time and the values that I obtained. And let me also plot it. Okay. Okay, this is my sinusoid plus noise. Okay, for 100 time step. Now I want to fit a random forest. Okay, it's also very easy in R, but here the complication is that I don't have only an explanatory variable. I need to lag the data in order to obtain additional explanatory variables that are given by the past data. So in order to express the current data, the current value that I simulated, depending on the past one, I have to lag the data of 1, 2, 3 time steps. And in particular here, I want to express the sinusoid plus noise, depending on the previous and the previous and the previous. So lag is 1, 2, and 3. And therefore, I need to add additional columns to the database. So now the data, if I make data 1, I have two numbers, time and the value, okay? Now I need to add 3 more columns. So the value lagged twice, and the value lagged 3 times. And this is obtained with these instructions. I'm not sure if you are familiar, I was not, with this instruction in R. This instruction in R, percentage greater percentage, means that you use the data on the left as the first argument of the function on the right. Okay, so basically what I do is to create, to mutate a data set by including the same data set plus the data, the lagged data. Okay, so let's try to, sorry. Okay. Okay, now let's look again, data 1. You see Y and A, because lag 1, there is nothing before the first observation. But if I go to 2, you see now lag 1, I got the previous. And now 3, and here we are, and 4. This function lag that I just applied, lag here, comes from dlibr, the library that I uploaded. You see, lag time series stats. Compute lagged or leading values, dlibr. You see here. Sorry, it's very small, but okay. Yes. Okay, good. Now my data set is ready, okay? And I could make it like 110, so you can see it, it's ready. Now I have to express the value depending on the 3 past values, okay? And I think here there is an instruction, NAOMIT, okay? We need this instruction because we need to remove the NAs. And let me see what is the result now. Okay, so basically it has removed the first 3 rows where there were NAs. Okay. Okay. Train size. Train size. This is basically saying that we need to omit 20% of the data, and in order to make the random forest, okay? And then here you see that there is the training data. Sorry, no, it's not like I just said, I make a correction. It is splitting the data in training plus testing, and it uses for training the first 80% of the data, and for testing the last 20%, because here it's also making a check of the capability of the random forest to predict the future data. And therefore, once again, I have this time series, the sinusoid. I'm using the first 80% to train the model, and I reserve the last 20% to, sorry, the first 80% to train the model, and I am reserving the last 20% to test the data. And indeed, what you see here is that test is the data set for testing. Okay, very good. Let's Copy this. So it's interesting here also to see how it works in prediction. Okay. Let me clear the screen at this stage. And now here there is the model. Random forest, it is trained, and these are the value for training, lag1 plus lag2 plus lag3, and M3 equal 2000. Here I'm not specifying the depth, okay, just the number of trees. This is something that I don't understand of this package, because the number of trees is not resolving over parameterization. A little bit, yes, because of course by random sampling we make the model more robust. But what is interesting, if one wants to reduce the number of parameters, is the depth of the tree, which is taken here by default. And we have the opportunity to fix the max depth, but actually it's not explicit, okay? I had to explore for it to find the option. This is the model which was trained, and now we make the prediction, and the prediction, you see that it asks for new data, and the new data are given by the test part which I selected. Okay, so this is prediction, and this is the RMSE which I got, okay, from the prediction. And if I want to see the value doesn't say much, because of course RMSE is not rescaled, and it doesn't say much. But in any case, this is the value, and now we can plot the test values and sorry, the predictions and the predictions. Here it is, actual predicted. This is in validation. Okay. Keep in mind that this is relatively easy because it's a sinusoid with a limited noise, so it's relatively easy. And you know, predicting a sinusoid based on the past observations, it's not so difficult. So, I mean, this simulation looks like it worked. Keep in mind, this is in testing, it's validation. You see that it's just 20 points, okay? It's the last 20%. Okay, very good. Let me just show you importance. What is importance? Let's see. So this is an estimation of the explaining power of the three variables. So lag1 got a score of 14, lag2 a score of 10, lag3 a score of 10. This means that the most important is lag1, and then lag2 and lag3 have more or less the same importance. It's a nice feature of random forest, which you can obtain also with other deterministic models. When you have multiple regressors, you can estimate the importance of each regressor. And this says basically that all of them are significant. In some of the cases, you may get an importance that is like 1/10 of the most important variable, and then maybe wise to discard it. Perfect. Let's now make an experiment by we can just cut and paste this one with let's take the same time series. So okay, same time series and same data test, but what I want to do is to change the number of trees, and let's see what happens. Model random forest, okay. The problem is that to change the number of trees, I have to start from here. Perfect. So number of 3, 2. Okay, let's see what happens. And then I can go down up to the end. First, you see the importance, lag 3, drop it down. And let's look at the, I don't understand why. Because it plotted the, okay. So I need to remake the plot of observed versus simulated. Okay, here it is. There is not a huge difference, but you see that it's more stepwise. You see that there are steps and more evident steps. And it's clear that it's the approximation is not as satisfactory. Now, let's make another experiment. Let's repeat all of it, and then we make the break. Let's repeat all of it by adding a lot of noise. And in order to repeat all of it by adding a lot of noise, it's better if I make a cut and paste first in a text editor, because otherwise, anytime I have to cut and paste it. Okay, now let me, you don't see anything here, so edit preferences and view. Or maybe I can just use this, perfect. Okay, so instead of 0.2, let's put a standard deviation of 1 in the noise. So we are expecting that the model becomes less effective. And I'm stopping here because the importance is not so relevant now. Okay, let's look at the plot. You see, it doesn't look like a sinusoid, and the prediction actually is not that good. But this is not a limitation of the model. It's just that we are trying to reproduce basically a noise, and therefore you understand that it becomes more difficult for the model. So I hope that at this stage you have a quite pretty good understanding of how it works. Random forest is extremely simple, extremely simple. And with these packages, it's extremely easy to train it. On the other hand, it's not so easy to change the default parameters for both of them in Python and R. And it's not also easy to understand how many parameters, because if you look at these codes here, you understand why my student, when I ask, but how many parameters here? And they cannot reply. Because when the model is defined, like here, model random forest, it says, okay, I want a random forest. The explanatory variables are lag1, lag2, lag3. And the number of trees is 200. But it doesn't say max depth, which is the relevant variable for getting the number of parameters. So if you use these models, you see it's extremely easy, but try to understand what's going on and ask yourself the question, did I understand for any single line what is doing this code? And if I had to write a code from scratch by using only basic R function, given that the concept is so simple because it's just a computation of an average, ordering the data, computation of an average. Am I able to do that? And if the answer is no, just try to understand why. And if what you are missing is just time, because it takes time, or if you are missing important knowledge. And remember, the questions are always, what about overparameterization? And what about the physical constraints? Is your model reproducing the physics of the process? And machine learning is much used to emulate climate models. And emulate climate models means that in order to reduce the computational requirements, because you see computational requirements is just 1/10 of a second, they try to substitute the physically based climate models, which takes months to run, with an emulation, an approximation with machine learning, which takes like minutes to run. It's important that they preserve the physical basis. So this is the question usually it is asked to you. over parameterization and the physical basis. So over parameterization, you can resolve with validation, but it's important that we validate. And physical basis, just keep in mind that we are not mentioning it, but you have the opportunity of constraining the results in order, for instance, to expect some physical constraints. So do you want to preserve mass balance? We can do that. Of course, you have to get the proper software and you have to be able to impose these constraints, but we can do that. In the remaining time, now we stop for about 15 minutes. In the remaining time, which is about half an hour, I'll give you another example of another machine learning. I don't think we have time to complete it, but it's another important example, I think. Perfect. I think we can stop here for 15 minutes. Thank you. I am closing I think the registration is here. Okay, it's still recording. And then
Thank you.
Okay. I need to close one micro, so it should work in this way. If you have any problem in listening or seeing the video, let me know. And let me just, okay, perfect. It's still recording, that's fine. So, machine learning, another example, neural networks. So, I think you are already familiar with the name because the neural network has been actually, at least according to my experience, the first type of model that I learned of. And it's a kind of emulation of what happens in a real neural network. So in what we think happens also in the brain. And in fact, these are called actually not just neural networks, but artificial neural networks. And the acronym is ANN. It's a deterministic relationship. And you see the scheme. The scheme is a connection between an input and an output. And the input can be just a single value or three values like here. And the output can be a single value or two values like here. And two values because the output may be, for instance, a vector. Like, for instance, for floods, we may predict the water flow and the water velocity. The idea is to relate with a straightforward relationship these inputs with the output, eventually, possibly, by passing through an hidden layer. An hidden layer is something that is between the input and the output. Maybe, for instance, like state variable. If you remember the bucket model, you pass from, for instance, rainfall to water flow through storage. And the storage is state variable. And the idea is here to use this hidden layer in a way to give more flexibility to the model and giving the opportunity then to simulate also intermediate variables like state variables. And the idea is that in any node of the network, we see here 3 plus 4 plus 2, 9 nodes. Any node is connected to neighboring nodes with a connection. And the connection, for instance, the hidden layer is connected to the input and the output. The input is connected to the hidden layer and the output is connected as well to the hidden layer. And the hidden layers may be more than one. And the connection is through basically linear relationship. So that, for instance, look at the blue arrows here. The first on the top node of the hidden layer is connected through three arrows, three links to the three inputs. And you see weights. The idea is that the content, the value of the top node of the hidden layer is a linear combination through the weights of the three inputs. And usually there is also in the node, once that the linear combination comes in, there is what is called an activation function. The activation function is a manipulation of the result of the linear combination in order to increase an additional flexibility. And this activation function is something that needs to be defined. Can be a sigmoid, it can be, we will see what a sigmoid is, but can be a function that rescales the input, the linear input. In any case, it's a transformation. And therefore, in any node, you have this transformation, which is called, once again, the activation function. The activation determines the output. So if you look, this is a bit, let me try to enlarge it, because this is small. And if you look at the blue connections, they go to the upper hidden node. And then from the hidden node, you see the two red arrows. And these are called activation weighted sum of the inputs. So the activation is this function, which is not displayed here. So first you get the weighted sum, and then there is the activation. And the activation goes to the two nodes of the output. And once that, for instance, the upper red arrow gets to the output, then it's elaborated in the output node, in the upper output node, through a linear combination of all the arrows that go into that node. So it is very simple, as you say. The only thing that we miss here is the values, if you want to apply it, and the activation function. But the activation function is just a transformation of the linear combination. And therefore, everything is extremely simple. But of course, if you take a large number of hidden layers, then it becomes quite complicated. And what are the parameters here? The parameters are the weights. The weights, usually the activation function is not parameterized. It's a function that works without parameters. So any arrow has a weight, and you see that there are many arrows. So at the end of the story, you get a lot of parameters. And this is the idea of the artificial neural network, which, by the way, sorry, I wanted to get here. By the way, it's nonlinear. It's nonlinear because the activation function will be nonlinear, and in general, therefore, we can introduce nonlinearity. Very good. The number of layers is arbitrary, and so as you see here, signals travel from the input layer, the first layer, to the output layer, the last layer, possibly passing through intermediate layers, which are called hidden layers. Very good. Now, there are several variants of this scheme, which generate specific models, specific types of neural networks. Let's look to a meaningful example, which is given by what are called LSTM, long short memory network, LSTM network. This is a very meaningful example. We explore a little bit how it works, and there are here below codes for the application, which I invite you to explore. I don't think we will have time to explore them. Maybe in the last lecture we can make some example of application, and I hope also to be able to propose an experiential learning and exercise with these networks. And why I choose this example? Because LSTM recently became extremely popular and increasingly applied, in particular in environmental sciences. Why? Because environmental processes, in general, all of them, exhibit correlation. And random forest model are not explicitly conceived for reproducing correlation. We can make it. We can adapt random forest to reproduce correlation. And we made the example of the sinusoid, which we model depending on the past data. So we made an example indeed, but actually this is not the purpose for which they were conceived. And there is also two things two considerations that I want to make. First, correlation is just a form of dependence. There is also another form of dependence, which is the long-term correlation. What does it mean, long-term correlation or long-term persistence? Here, there is a link, long-term dependencies. This phenomenon is identified with several synonyms: long-term correlation, long-term persistence, long-term dependence, and Hurst effect. Let's look at one of these links. I think this is the same. Yeah, okay. Long-range dependence, also called long memory, I forgot to say another synonym, or long-range persistence, is a phenomenon that may arise in the analysis of spatial or time series data. It relates to the rate of decay of statistical dependence of 2 points with increasing time interval or spatial distance between the points. A phenomenon, let's read this, is usually considered to have a long-range dependence if the dependence decays more slowly than an exponential decay. It's typically a power-like decay. This means that dependence is preserved between observations that are far apart in time. Okay? It's a kind of memory that lasts for a long time, and we know that in climate, for instance, there are cycles. The cycle is a typical effect of long-term dependence. So long-term dependence, long memory is extremely important sorry, I need to go down, in environmental sciences. Okay, perfect. Let's look also the second link, Hurst effect. It's also a synonym of it, and actually, Hurst identified, he was an hydrologist, and I think it's interesting to learn the details of the career of this man, because he basically identified a model for measuring the intensity of long-term memory and identified a model to simulate the long-term memory. We stop here, okay? But it is very interesting. It is very interesting. And then I want to mention another problem for neural network to model longer-term dependence. And the problem is called the problem of the vanishing gradient. So let me open a Google vanishing gradient to show you that indeed this is, now it's in Italian. So you see the links, vanishing gradient in deep neural network. And then vanishing gradient problem, Wikipedia, vanishing gradient problem, okay. It's not easy to read it on Wikipedia. It requires more time than a simple explanation that I want to give you. So suppose that we want to calibrate this network, okay? What we do is, as usual, we start from the input, go through the network, get to the output, compare root mean square error, and then we find an error. Then how it is the network trained? I go backwards. So I have an error. I go to the hidden layer and I try different weights for the hidden layer. And then from the hidden layer, I go to the input layer and I try to find the optimal weights for the input layer. Okay? To minimize the error. What is the problem? The problem is that in moving backward, from the output layer, from the hidden layer, I have a high gradient of error. This means that when I compute the partial derivative of the error with respect to the weight between the output and the hidden layer, the partial derivative is large. There is a gradient, there is a large variation. So the weight from the hidden to the output layer explain a lot of it. Then once a lot of it has been explained, when you go from the hidden layer to the input layer, the remaining gradient is very reduced, it's vanished. And therefore, this means that in the calibration, basically, there is the risk that the network says it's just correct the weight from the hidden to the output layer and forget about the weights from the input to the hidden layer. I think this is also the problem that we experienced with the experiment that I made with the random forest to reproduce the sinusoid. In the first attempt, the importance of lag3 was high. In the second attempt, the importance of lag3 was much lower. I think, given that I reduced the number of trees, it was a vanishing gradient problem. I'm not really sure. We could think about it. But indeed, there is this problem, which emerged clearly from the application of neural network. And therefore, people tried to make the structure of the network more complicated in a way to store past information. Because storing past information means that when you calibrate and go backward with the network, you still preserve the capability of taking into account what has been observed a lot of time earlier. So this is the idea. So how does it work then? Here I made a scheme, okay? So basically, what is the essence of LSTM? Is a unit, and let me just show you the screen here, the figure here. So it's a unit. It's a unit that makes several computations. And in this unit, we get with the input data, and then we exit from the unit with the output. Let's look at how the unit works. It is simple, but to explain it is not so simple because there are several computations that are made. But first, let's try to look at the textual description, okay? So first of all, the input is X, and the output, let's call it output now. It's not necessary that we identify it with a symbol at this stage. It's the input. Now, the unit is composed by several computations. Some of them are called gates. Gates because they are like gates from which the input data get into the unit, etc. So there is a first gate, which is called the forget gate. The scope is to decide what information to discard from previous memory. Depending on some state of the unit, some state that we will see how it is computed. And we call this state H. It's called hidden state because it's not something that we see. Actually, as you will see, at a certain point, we see it. But anyway, it's called hidden state. And it is observed at any time step. The forget gate looks at the state at the previous time step. And this is H, I cannot select it, but H t minus 1. And looks at the current input. And it makes a weighted average through two weights. So the response is a value between 0, forget everything, and 1, keep everything. Because there is a linear transformation first of ht minus 1 and xt, followed by a sigmoid function to rescale it in the range 0, 1. So the sigmoid function, it's a very simple function. You can see some examples here. But look at the graph. It's the logistic curve is a sigmoid function, makes a transformation of the data in the range 0, 1. Okay. So let's forget about the sigmoid function now, because it's a very classical function explained in mathematics, and it's non-parametric. It just takes the linear transformation of hidden state previous time and input variable at the current time, and then this linear transformation is rescaled in the range 0, 1. Very good. And 0 means forget everything about the past. 1 means keep everything. Very good. Input gate, it does the same thing, okay? And let me just, okay. Input gate, sorry, I needed to refresh the page because I modified it recently. Input gate decides what new information to store in the current hidden state. It depends, again, on the previous hidden state and current input xt. So it makes the input gate the same transformation through a linear function and then a sigmoid function. But then the input, the result, is used in a different way with respect to the forget. And therefore, they don't take the same shape. Because when we optimize weights, it turns out that the forget gate has different weights with respect to the input gate, okay? Very good. Now there is a computation of a candidate new information, which is an intermediate step to compute what is called the cell state. First, we identify this candidate, which depends on the previous hidden state and the current input again. And then the result is rescaled, this time by the hyperbolic tangent. because we want values in the range -1, 1, not 0, 1, -1, 1, and therefore we use the hyperbolic tangent. Next step, we compute a cell state depending on what? On the forget gate, input gate, FT, IT, depending on the candidate new information, and depending on the same cell state at the time t-1. And here there are functions, and basically they are weighted linear transformation. We will see the details. And then there is an output gate, which is not delivering the output actually. It decides what to output by computing a value, OT, that depends again on HT-1 and XT. And then it is scaled. I forgot to write here the sigmoid function in the value 0, 1. And then there is the final output, which is computed depending on what? Depending on the output gate. Here there is a missing T. I needed to make a correction here. Depending on FT is the forget gate, and depending on the new state CT. And here there is, okay, first of all, a summary step by step. So what they do is compute the amount of all the information to be forgotten, add new information, and compute the output. And then the scheme is reproduced here, but still there is no here explanation of the analytical formulation of it. And then here there is a numerical example, which allows you to understand how computations are done. So let's go here. Then the computation is articulated along the following steps. For get gate, I compute FT, and FT is a sigmoid of a vector of weights, WF, times a vector of including previous hidden state and current input plus a bias. So here we have already 3 parameters. WF is a vector of size 2. The bias is the third parameter, and therefore we can make the computation. And the computation is done by taking for the bias and the weights the values that are given above, just for making an example. And then compute the sigmoid. Perfect. And the result is 0.66, namely keep 66% of all the memory. Very good. Let me correct that. I think that for 5 minutes you can use. Input gate, a similar computation. You see HT-1 XT plus a bias, and here there is a sigmoid, and you can compute it. Candidate representation of new information. There is the hyperbolic tangent. Again, function of HT-1, XT, and the bias. And then there is the update of the cell state with a simple linear computation. And then there is the computation of the output gate, a sigmoid of, again, a linear combination of HT-1, XT, and then the final result, which is given by the OT times the hyperbolic tangent of CT. And then if you take these numbers, you get this final result. We stop here with some final considerations. It looks a bit complicated, I mean, but it is the result of an attempt to give more flexibility in order to keep track of the old memory of the process. Indeed, when you come to the computation of the number of parameters, they are essentially weights and biases. It's very large because also a network is composed by more than one unit in general. This is one parameter that you can decide. And A network with two units has twice the parameters of a vector network with one unit. And as I said, it looks complicated and it's difficult to understand the reason why they decided these complications, but actually it was a step of subsequent developments in order to obtain a structure that proved to be able to preserve the whole memory, the long memory of the system. Even for these networks, we have R and Python packages, and here you can find codes. If you go down, there are more than an example, step by step, and then there are codes here for applying two variants of the same network. I think, yeah, there are two codes. And therefore, I mean, again, it's, and there is another example code here. It's very easy to be applied. Again, it's important that you understand how it works. We don't go into details. I just wanted you to know two examples. Random forest is, the structure is easier than LSTM. LSTM, if you want to model time series, is most recommended. So if you look for applications, basically you see that it's most recommended and most used. Once again, here the problem is overfitting. Now we are trying over the Po River because we have models based on the physics of the system, which count like 10, 11 parameters, which work quite well. And now we are trying with these random forest and LSTM, and we are struggling to identify what is the best structure, number of nodes, number of max depth, or the depth of the tree, or the number of the units of the LSTM. We are struggling a little bit because indeed we experience overfitting. So when we calibrate, everything works perfectly. When we go to validation, there are problems. I just want to say that if your purpose is to make prediction with the lowest uncertainty, what we discussed so far is perfectly fine. So we have to avoid overfitting. But if, for instance, your purpose is trying to understand a pattern, so trying to understand the shape of a signal between an input and an output, you may discard the problem of overfitting. You just want to identify the deterministic model that reproduces the pattern. And in this case, you can, if your purpose is not to make a prediction, you can just discard it. The only thing it is that you need, especially if you want to understand, is to really get aware of what the model does, because otherwise you don't understand anything. You just see that the model works well, but you don't understand for what reason. Okay, okay, that's my introduction to machine learning. And again, we meet next time, May 20, in Bologna. So this is the last lecture in Ravenna. And I tell you the room. And May 20, there will be a seminar of one of my PhD students on machine learning application to groundwater modeling and Po River modeling. And I hope also to have the opportunity to present an example of application to the Po River, which you may repeat. And that's it. Thank you very much for your patience.
Thank you, Professor.
Bye-bye.
See you.
Professor.
Bye.